Good morning, class. Let's continue with the topic. Representation of an electrochemical cell. Representation of an electrochemical or galvanic cell. So last class we spoke about the setup of the electrochemical cell. It consists of two half cells, that is oxidation half cell, reduction half cell. Okay, there we spoke about what is redox couple. Okay, we spoke about the flow of the electrons from anode to cathode. Oxidation occurs at the anode, reduction occurs at the cathode. Anode has a negative polarity, cathode is positive over here, and the current flows from cathode to anode. Right, so this we did in the last class. Now basically how to represent an electrochemical cell with the help of some notations. So left hand side anodic compartment will be present. Left hand side anodic compartment will be present. What's the meaning of anodic compartment? Anodic compartment means components of oxidation half cell. Components of oxidation half cell. That is, if you refer to the previous example that we did in the last class, that is zinc rod in zinc sulfate solution was my oxidation half cell, if you remember that, right? And these two represents oxidation half cell, right? Now these two parts are separated by a single vertical line, that is zinc vertical line, ZnSO4 aqueous. Either this or we can write Zn2 positive aqueous. Because zinc sulfate means it is Zn2 plus, because sulfate ion doesn't take part in the reaction. So this way I represent my oxidation half cell, that is the anodic compartment, that is on the left hand side. Now right hand side will be my cathodic compartment. Right hand side my cathodic compartment. That means components of the reduction half cell. Components of reduction half cell. So here the example I'll give, that is the same thing that we did in the last class. It is copper in copper sulfate solution. Copper in copper sulfate solution. Now how do I represent? Again this two part I have to separate by single vertical line. So I'll be writing copper sulfate solution, vertical Cu, or I can write Cu2 positive aqueous, then Cu. This is my representation of reduction half cell. Now in case of oxidation half cell, Zn was on the left hand side and Zn2 positive was on the right hand side. Here we have Cu2 positive on the left hand side and Cu on the right hand side. Why? Because in oxidation half cell, oxidation occurs. That means Zn will get converted to Zn2 plus. That's why we are writing this on the right hand side of this line. In case of reduction, Cu2 positive gets converted to Cu, right? So this we are writing on the left and the final product we are writing on the right of the vertical line. Now we will write the entire notation. So Zn solid, because it's a metal rod, vertical line Zn2 positive aqueous, and reduction half cell we are going to write Cu2 positive aqueous, Cu solid. And these two half cells, they are separated by a salt bridge, they are connected by a salt bridge which is given by double vertical line. This represents my salt bridge. So this is basically representation of an electrochemical cell. If I get this type of notation, I can understand this left side is my anodic part, right side is my cathodic part. Anodic part means this is the oxidation, this is the reduction. So I can easily write the cell reaction, right? I can easily understand from here that my cell reaction, that is oxidation half cell reaction, will be what? Oxidation half cell reaction will be Zn2 positive plus 2 electrons. Reduction half cell reaction will be my Cu2 plus 2e arrow Cu. Right? So what is my net reaction? Net cell reaction? It will be, how do I write the net cell reaction? It will be Zn plus Cu2 positive arrow Zn2 positive plus Cu. That means I have to add these two equations. Okay, then 2e will get cancelled and we are going to get this final thing. So this is my representation of an electrochemical cell. Next one, we have electrode potential. What is this electrode potential? Electrode potential. Now, when a metal rod is in contact with solution of its own ions, okay, is in contact with solution of its own ions, then there are two processes that occurs. Number one is tendency of metal atom to form positive ions by losing electron. That is, this process is basically what? This is oxidation of the metal. This is the first one. That is when a metal rod is dipped in solution of its own ions. In that case, we get to see two opposing processes. Right, first process is basically oxidation and second process is reduction. That is tendency of metal ions to gain electron and get deposited on metal. So this is basically reduction. Right, so these are my two opposing processes, oxidation and reduction. So these two will occur when a metal rod is in contact with its own solution. Now, suppose if process 1, if process 1, rate of process 1, that means rate of oxidation is more than rate of reduction. If this is the first one, if this is the first case or the first condition, when rate of oxidation is more than the rate of reduction, then what is the common thing we are going to get? Concentration of metal cations will increase. Concentration of metal cation will increase because more and more metal will lose electrons to form cations. So concentration of metal cation will increase. And what is the other thing? Excess accumulation of electron at metal rod or metal electrode. So this too will happen when rate of oxidation is more than the rate of reduction. So if this is the condition, then what we are going to observe? There will be negative charge at the electrode. Okay, and since in the solution the concentration of metal cation is increasing due to the rate of oxidation being faster, so close to the electrode we are going to have positive charge. Okay, positive charge means it represents the concentration of cation increasing, right? But throughout the solution is electrically neutral. Throughout solution is electrically neutral, means solution contains equal number of cations and anions throughout. Okay, now this scenario is closer. This is plus and minus, okay? That means cations and anions. If I have zinc sulfate solution, I'll be having Zn2 plus and sulfate ions. It is basically, this scenario is closer to the metal rod. Now what is this region known as? This region is known as, the interface. It's only at the interface point we get to see this combination of positive and negative charges. Right? Interface means what? It is the point where the metal rod is in contact with the solution of its own ions. Only at that point, means this point only we are going to get this positive and negative charge combination, and this is known as electrical double layer. Electrical double layer, why? Because it has combination of both charges, right? Throughout the solution will be electrically neutral. It is only at the interface we are going to have this combination of positive and negative charges that represents the formation of electrical double layer. Now this electrical double layer formation only gives rise to the electrode potential, right? In case of second one, that is second condition, when rate of reduction will be more than rate of oxidation. If rate of reduction is more than oxidation rate, if 2 is more than 1, then what happens? Your concentration of metal cation will decrease, okay, and electron density at metal rod or metal surface also decreases. Why? Because more and more cations will gain the electrons and get converted to the neutral metal. That's why concentration of cation will also decrease and the density of the electrons at the metal surface will also decrease. So what is the scenario then? And the scenario is this one. As the concentration of the electrons at the metal rod decreases, that means they are going to have positive charge at the metal surface, and since the concentration of the cations in the solution is decreasing, so I represent that by negative sign. Right? Throughout my solution will be electrically neutral. Right? It is the charge formed only at the interface. It is a double layer formed at the interface. Electrical double layer at the interface. Interface means the point at which the metal rod is in contact with the solution of its ions. So this gives rise to electrode potential. When I talk about electrode potential, we have two types of electrode potential. What are they? First one is oxidation potential. And the second one is reduction potential. Oxidation potential means it is a tendency. Oxidation potential, it is a tendency of an electron to lose electron, right? And reduction potential represents the tendency of an electrode to gain electrons. It is the electrode tendency to lose electrons. This is the electrode tendency to gain electrons. Basically, we are speaking here about anode, and here we speak about cathode, right? Because at anode only we have oxidation, at cathode we have reduction. Okay. Now we need to know this for a given electrode, for any given electrode, whether it be zinc electrode, copper electrode, anything. Oxidation potential and reduction potential value will be similar in magnitude but opposite in sign. Okay. For a given electrode, oxidation and reduction potential values will be same, but their signs will be opposite. Right? For example, if I talk about copper electrode, suppose its oxidation potential value is 5. That means reduction potential value will be -5. That is, they will have same values but opposite in signs. That's what I meant. As per modern conventions, we have to consider only the reduction potential. We are going to consider this values. Means whatever sums we do, we are going to consider this reduction potential values and not the oxidation potential values. Okay. Now we come to the factors. The factors are, first one, factors on which electrode potential depends. First one is your nature of electrode, whether it be active or inert. Second, we have concentration of ions in solution. Third is your temperature. So these are the factors of electrode potential. So thank you, class.